Hey there, and welcome to the Quantum Slumber. I'm glad you found your way here tonight. Whether you're lying in bed, half under the covers, or just looking for a quiet moment to let your mind drift, this little corner of the internet is where we take the strangest ideas in physics, slow them down, and turn them into gentle stories you can fall asleep to. In your day-to-day life, reality feels stable. If you shove a chair, it moves. If you let go of a mug, you don't worry that it might hover in the air or split into two copies. You expect the world to follow the same rules today that it did yesterday, and most of the time, it does. That's the comfort of the everyday world. It behaves. But every now and then, you stumble across something that doesn't quite fit. You read an article, or see a headline, or hear a video talking about particles being in two places at once, about experiments where the outcome seems to depend on a choice made later, about measurements that don't just reveal what's there, but somehow change what's there. And maybe, at first, you shrug it off. You tell yourself, that's probably just how the math works. It's only weird on paper. In real life, things can't possibly be that strange. You mentally file it away as one of those science phrases, like a riddle that doesn't really touch your everyday world. But if you look a little closer, the story becomes harder to ignore. These ideas aren't just wild metaphors or sci-fi plots. They come from real experiments, done with real equipment, by real people, in real laboratories. They've been repeated, checked, and confirmed. The numbers line up. The devices behave the same way again and again. The weirdness doesn't go away when you measure it more carefully. It gets sharper. That's where the unease starts to creep in. Because the problem isn't that these experiments don't work. They work beautifully. The problem is that no one can fully agree on what they mean. Different physicists look at the same results and tell completely different stories about what's actually happening underneath. Some say it's all just probabilities and bookkeeping. Some say the universe is constantly branching into endless versions of itself. Others think that what we call reality doesn't fully crystallize until someone, somewhere, makes a measurement. And these aren't fringe ideas whispered on internet forums. The greatest minds in physics, people like Einstein, Schrödinger, Feynman, and many others, looked at the quantum world and openly admitted that it left them unsettled. They could write down the equations. They could use them to build lasers, computers, and MRI machines. But when they asked, what is this actually telling us about reality itself? The answers started to fall apart. In a moment, we're going to step into that discomfort together. We'll explore some of the strangest quantum paradoxes that scientists have found, puzzles so deep that they don't just challenge our theories, they challenge our sense of what is real. If you enjoy drifting off to quiet stories like this, where science meets gentle wonder, you can always subscribe or tap the like button, or leave a comment later to tell me what you think. There's no rush. For now, you can just relax and listen. Let the ideas wash over you, because here's the quiet, unsettling possibility at the heart of tonight's journey. If these experiments are really telling us the truth, if the quantum world truly works the way the data suggests, then the universe you thought you lived in, the simple, solid cause and effect world, might not be the whole story at all. In everyday life, when something doesn't make sense, you might call it a puzzle, a riddle, a brain teaser you can solve if you just think hard enough or get the missing piece. That's how a lot of people imagine quantum physics too. They hear the word paradox and picture a clever trick, something strange on the surface, but harmless underneath. If we just had the right explanation, the weirdness would disappear and the world would go back to normal. But in quantum mechanics, paradoxes aren't just party tricks. There are places where our picture of reality actually cracks. In the classical world we're used to, things behave. If you throw a ball, it follows a smooth curve through the air. If you flick on a light, the bulb glows in a steady, predictable way. You might not know every detail, the air resistance, the exact path of every electron in the wire, but the overall behavior is solid. Newton's laws and later Einstein's relativity describe a universe where events line up in a clear chain, cause, then effect. When physicists shrank their focus down to atoms, electrons, and photons, they expected the same basic logic to hold. Maybe calculations would be harder. Maybe there would be more tiny details to keep track of. But the underlying idea that with enough information you could predict what happens felt safe. Quantum mechanics quietly takes that comfort away. At the smallest scales, even with a perfect description of the system, you can't say exactly what will happen next. You can only say what might happen, and with what probability. The equations don't tell you, this will happen. They say, here are the odds, and here's the twist. Those equations work astonishingly well. They power the devices you're surrounded by. Electronics, lasers, MRI machines, GPS systems, and more. If you're holding a smartphone or lying near a Wi-Fi router right now, you're already living inside quantum theory's success. The paradoxes appear when we ask the next question. If the math works so perfectly, what kind of world is it actually describing? That's where things stop fitting neatly together. We get situations where particles seem to be in multiple states at once, then suddenly pick one when we look. Experiments where the outcome seems tied to choices made later. Setups where two observers describe the same event in completely different ways, and both descriptions are supported by the theory. Different physicists tell different stories about what all this means. Some say the wave function is just a tool for calculating probabilities. Some insist it's something real, a physical field of possibilities. Others think reality splits into countless branches, with every outcome happening somewhere. None of those stories feels entirely comfortable, and the tension between them, that mismatch between flawless predictions and murky meaning, is what we call a quantum paradox. Not a mistake in the math, but a sign that our understanding of reality itself might be missing a few pieces. If you follow these strange quantum stories long enough, you keep bumping into the same quiet troublemaker, measurement. On paper, a quantum system is beautifully simple. You don't say, the electron is right here, moving this fast. Instead, you describe it with a wave function, a gentle smear of possibilities. It might be here, or there, or somewhere in between. It might be spin up, spin down, or a mixture of both. Before you look, it isn't in one definite state. It's in a superposition of many. That word, superposition, sounds abstract, but the idea is brutally direct. The theory doesn't say, we don't know which option is true. It says, until you measure, there is no single option. Then you perform a measurement. You check where the electron is or which way it's spinning, and suddenly the hazy spread of possibilities collapses into one outcome, one position on a screen, one click in a detector, one result written in a notebook. The math jumps from many maybes to, this is what happened. That jump is the heart of the problem. The equations of quantum mechanics tell you exactly how the wave function flows and evolves until the moment of measurement. At that point, the math falls silent. It doesn't say how the collapse happens. It doesn't say why this outcome instead of that one. It doesn't even tell you when something counts as a true measurement. Is it enough for a particle to hit a sensor? Does it require a macroscopic device, something heavy and clunky? Does a human observer have to look at the data? Does consciousness matter at all? Or does the universe in some strange way notice itself? Physicists have been circling these questions for decades. One legendary figure once admitted that nobody really understands quantum theory, not in the way we understand a falling apple. Another warned that if you encounter quantum mechanics and you're not shocked, you probably haven't grasped it. Others, Penrose, Einstein, Schrödinger, voiced their own discomfort, calling the theory baffling, incomplete, even something they wish they'd never touched. And yet, they all agreed on one thing: the calculations work. That's what makes the measurement problem so unsettling. We have a theory that predicts outcomes with incredible accuracy, that quietly runs underneath modern technology. But the moment we ask what is actually happening when a possibility becomes reality, the ground starts to crumble. Quantum paradoxes live right in that gap. They're not just quirky footnotes or clever puzzles for late-night debates. They're more like tiny fractures in the story we tell about the world, small breaks that hint that the narrative itself might be wrong, or at least unfinished. And if you trace those fractures carefully enough, they lead to a disturbing, fascinating question. When we look at the world, are we discovering reality, or helping to decide which version of reality gets to exist? Imagine you're at a small pond on a still evening. You pick up a stone and toss it into the water. Ripples spread out in perfect circles, overlapping if you throw in a second stone. The pattern on the surface tells a simple story. Something disturbed the water here, and the waves met in between. Now shrink that picture down to the scale of a single particle of light, a photon. Instead of stones and water, you have a tiny source that fires one photon at a time toward a screen. Between the source and the screen sits a divider with two narrow openings, two possible paths the photon can take. This is the famous double-slit setup. If you don't try to check which slit the photon goes through, something strange happens. You send the photons one by one, but over time, the pattern on the screen doesn't look like two simple bands, the way you'd expect if tiny particles were just flying straight through. Instead, you get an interference pattern, bright and dark stripes, as if each photon were a wave that passed through both slits at once and interfered with itself, just like ripples on a pond. But if you place a detector at the slits to ask, which path did you take? The pattern changes. Now the photons behave like ordinary little bullets. The interference disappears, replaced by two smeared-out clusters behind the slits. Somehow, the mere possibility of knowing the path destroys the wave-like behavior. The particle seems to be saying, if you insist on knowing where I went, I'll stop doing the wave trick. So far, that's already unsettling. A simple question. Which way did it go? Seems to change the outcome. But you can at least tell yourself a story. Maybe the act of measurement disturbs the system. Maybe the photon was always going through one slit or the other, and the interference was just a quirk of the math. The delayed choice quantum eraser makes that comforting story much harder to hold on to. To ease into it, imagine you modify the experiment. Instead of letting the photon hit the screen directly, you use a crystal that splits it into two partner photons, entangled with each other. One of them, the signal photon, heads toward the screen and makes a dot. The other, the idler, takes a more complicated path through additional mirrors, beam splitters, and detectors. Here's the key twist. By adjusting the setup for the idler photon, you can choose whether or not to preserve information about which slit the original photon effectively took. In some configurations, the idler carries a mark that, in principle, lets you trace the path. In others, that path information gets scrambled or erased, so you can no longer tell. The timing is where things get deeply uncomfortable. You arrange the apparatus so that the signal photon hits the screen before anything decisive happens to the idler. The spot appears on the detector. The event, in any everyday sense, is over. Only afterward do you choose which configuration the idler will encounter, one that keeps which path information, or one that erases it. When you collect many of these events and then sort the data, two patterns emerge. If you group together all the signal photons whose partners carried intact path information, you get a particle-like distribution. No interference, just a pattern consistent with either slit A or slit B. If you group together all the signal photons whose partners had their path information erased, you see an interference pattern emerge in the statistics, as if those photons had behaved like waves, exploring both paths at once. Remember, the signal photons all landed on the screen before you made your final choice about the idlers. The raw screen, taken by itself, doesn't show a clean interference pattern. It's only when you look back and sort the dots according to what later happened to their partners that the wave-like and particle-like subpatterns appear. It feels uncomfortably like a decision made in the present is reaching back and changing how the past looks. To be careful, this doesn't mean the screen magically rearranges itself, or that you can send messages to your earlier self. You can't stand at the screen, watch dots appear, and know in advance which ones belong to the wave group and which belong to the particle group. The interference only shows up after you compare the two streams of data and see how they correlate. Still, the logic is hard to shake. The same set of earlier events can be organized into two entirely different stories, wave-like or particle-like, depending on a choice made later. The past doesn't seem to be a fixed, independent record. It's more like a flexible script that only becomes clear when both the beginning and the end are taken into account. Some physicists try to soften the blow by saying nothing actually travels backward in time. They argue that the wave function, the mathematical object describing the whole setup, already contains all the possibilities from the start. Your later choice just determines how you slice up the data, how you read the script, not how it was written. Others lean into the discomfort. They explore interpretations where time is not a one-way flow, but a kind of tapestry. In that picture, what happens later can help define how we describe what earlier meant, not by changing events, but by completing the pattern they form. Past and future act together to shape the story. Whichever explanation you prefer, the feeling is similar. The delayed choice quantum eraser doesn't just tell us that observation matters. It hints that our decisions about what to observe and what to ignore reach deeper into the structure of events than our intuition is comfortable with. The line between before and after gets blurry. The idea that the universe simply evolves forward step by step, with a clean trail behind it, starts to wobble. For a world that seems, on the surface, so straightforward, you drop something, it falls. That's a disturbing thought. A single experiment, repeated many times, whispers something strange, that the way reality appears may depend not only on what happened, but also on how and when we choose to look. Most of the time, we don't doubt that there is just one shared reality. If two people watch a glass fall off a table, you expect them to agree on what happened. The glass slipped, it hit the floor, it shattered. There might be small differences in how they describe it, but beneath all those details, there's one event, one set of facts. The glass broke. We build our whole sense of sanity on that idea, that there is a world out there that exists in a definite state, whether or not anyone is looking. Observers might disagree about opinions or memories or meaning, but not about the basic facts of a physical event. Wigner's friend is a thought experiment that quietly pulls on that assumption until the seams start to show. Picture a simple physics lab. Inside the lab, with the door shut, is a person we'll call the friend. They have a quantum device on a table, maybe a machine that measures the spin of a single particle, with only two possible outcomes, up or down. There's a screen that will flash one of two messages, and a notebook where the friend can write down what they saw. Outside, the lab stands Wigner, the physicist who first imagined this scenario. He can't see inside. The door is closed. He only knows that at a certain moment, the friend will run the experiment, read the result, and record it. From the friend's point of view, everything is straightforward. They prepare the particle, they press the button. The device interacts with the quantum system, and the screen flashes a result. For the friend, the superposition, the blur of possibilities, is over. They see spin up, or they see spin down. They write it in the notebook. They could call someone on the phone and say, "I've got the answer." They now live in a world where one specific outcome has happened. From inside the lab, reality has collapsed into a definite story. But from Wigner's point of view, outside the closed door, nothing like that has happened yet. He hasn't opened the lab. He hasn't looked at the screen. He doesn't know what the friend saw. According to the mathematical rules of quantum mechanics, he is allowed, almost encouraged, to treat the entire lab as one big quantum system. Not just the particle, but the measurement device, the flashing screen, the notebook, and even the friend's brain state are all part of a single wave function. In that description, there is no single, definite outcome yet. There is a superposition of two branches, one where the particle is up. The device says up, the notebook says up, and the friend's brain has the memory "I saw up," and one where the particle is down, the device says down, the notebook says down, and the friend's brain remembers "I saw down." From the outside, both branches are still present as live possibilities in the wave function. Wigner can, in principle, even design an experiment that interferes these two branches, treating "friend who saw up" and "friend who saw down" as components of one bigger quantum state. So, inside the lab, the friend feels that a single outcome has happened. Outside the lab, Wigner still describes the whole situation as a cloud of possibilities that has not yet collapsed. Who is right? It's tempting to dismiss this as a trick of language. You might say, well, of course there's a single real result, we just don't know it yet. Wigner's description is just about his ignorance, not about reality itself. That's how we handle uncertainty in everyday life. If a coin is flipped in another room, you might say it's 50-50 heads or tails. But you don't mean the coin is literally in both states at once. You mean you just don't know which one is true. Quantum mechanics is different. When you follow the formalism honestly, before any measurement, the system isn't just unknown. It really is in a superposition, a state that is not simply either up or down, we just don't know. And when you include the measuring device and the friend in the math, they become part of that superposition too. The unsettling part is this: the friend feels a definite result. They experience a world in which the ambiguity is gone. They could swear under oath that they saw up, for example. For them, there is no superposition anymore. But Wigner, if he sticks to the rules of the theory, is told to treat the friend as still being in a quantum blend of saw up and saw down until he opens the door and has his own measurement-like interaction. So there are two descriptions of what is happening. One in which a clear, definite event has taken place inside the lab. One in which no single outcome exists yet, only a set of overlapping possibilities. Can both be true? Is there one objective fact about what happened in the lab? Or is the fact itself somehow tied to who is doing the observing? For a long time, Wigner's friend stayed in the realm of thought experiments, an uncomfortable idea, but still just an idea. Then, in recent years, physicists built simplified versions of this scenario using photons and clever detectors, creating situations that mimic observers recording different outcomes within a shared quantum setup. The details are technical, but the broad message is surprisingly direct. If we insist that measurements always have single, observer-independent outcomes, and no information travels faster than light, and quantum predictions are correct, then we run into logical contradictions. Something has to give. One option is to relax the idea of a single, observer-independent reality. Instead of one universal list of facts, we have facts that are meaningful relative to each observer's frame. Inside the lab, the result is up is a fact for the friend. Outside the lab plus friend is still in superposition is a fact for Wigner. Both descriptions are internally consistent, but they do not merge into a single, neatly aligned picture. That's deeply at odds with everyday intuition, where we assume that if two people disagree about what happened, at least one of them must be mistaken. Quantum mechanics opens up a more unnerving possibility, that what happened may not be a simple global thing at all. Another path is to change the theory. Some interpretations say that wave functions never represent physical reality, only our knowledge. Others say that the wave function of the universe does branch, and that both outcomes, friend saw up, friend saw down, exist in separate parallel histories. In that view, Wigner's superposition is not a fog of possibilities, but a structure of many coexisting realities, and each observer only ever experiences one branch from the inside. There are also ideas that modify the rules so that large systems like labs and people can't stay in superposition for long. In those models, some physical process forces a single outcome, making Wigner's description incomplete. But those proposals come with their own challenges, and we have not yet seen clear experimental evidence for that kind of objective collapse. No matter which way you turn, something important has to be sacrificed. either the solidity of a single, shared reality, or the completeness of quantum mechanics, or the comforting idea that observing a system simply reveals a pre-existing fact. Wigner's friend doesn't give you a tidy resolution. It holds up a mirror instead. It asks you to sit with two people who both have good reasons for their stories. One is certain a specific event has taken place. The other is equally certain that no single outcome has yet crystallized. If the universe can support both descriptions at once, at least for a while, what does that say about the nature of facts? About the point at which possibility becomes truth? About whether reality is something out there, fixed and independent, or something that quietly takes shape in the relationship between a system and the beings who look at it? Those questions don't have easy answers, but letting them linger gently at the edge of awareness already changes how the world feels. The next time you and someone else watch the same simple event, a light turning green, a book falling closed, you might find a small echo of that sealed lab in the back of your mind, and the faint, unsettling thought that even here, in the everyday, the story of what really happened might be more delicate than it seems. Time feels like the one thing in life that refuses to bargain with us. You get older, coffee cools, a plate slips from your hand, hits the floor, and shatters into a pattern of tiny shards that no one, anywhere, has ever seen before, and will never see again in exactly the same way. You can almost feel the direction in all of that. Forward, from before to after, from not yet to already happened. If you mix cream into your coffee, the swirling white tendrils spread and fade until everything is the same soft color. You never sit at a table and watch the opposite happen, a uniform tan suddenly separating itself into pure black coffee and a floating, untouched pool of cream. The movie of your day never rewinds on its own, so it's natural to think that time itself has a built-in arrow, that the universe is somehow wired to move from past to future, never the other way around. But when you look at the basic equations physicists use to describe the world, the deep rules underneath the broken plates and the cooling coffee, those rules are strangely neutral about direction. If you take many of the core equations of physics and quietly flip the sign of time, running them backwards instead of forwards, they still make perfectly good sense. They don't protest. They don't scream. To them, a movie of particles spreading out looks just as valid as a movie of particles gathering in. The mathematics, in other words, doesn't care which way the film is playing. We already brushed up against this when thinking about the delayed choice quantum eraser. In that experiment, you send particles through a setup, let them hit a screen, and only later decide what kind of measurement to make on a distant partner system. When you go back and sort the data based on that later choice, you find interference patterns hiding in the statistics, as if the universe waited for you to make up your mind before it decided how the earlier events should look. Nothing on the screen visibly changes. You don't watch the dots shuffle around in real time, but when you regroup them according to the choice made in the future, a different story emerges from the same past. It's very hard not to feel, at least emotionally, that something about the flow of cause and effect has been disturbed. Of course, physicists are careful here. They'll remind you that you can't use this kind of setup to send a message back in time. No matter how you arrange things, no one can stand at the earlier screen, read off some pattern, and know what choice will be made later. There's no way to warn your past self, or win the lottery, or undo a mistake. And yet, these experiments don't sit comfortably inside the picture in which causes always live strictly in the past and effects always live strictly in the future. The correlations seem to be woven from both directions at once. That's where the idea of retrocausality enters, not as a science fiction time machine, but as a different way of thinking about how quantum events are stitched together. In a retrocausal picture, the universe doesn't build its stories using only initial conditions, like the starting frame of a movie. It also uses final conditions, like the last frame. The outcome you choose to measure in the future acts a bit like a boundary that reaches back and helps shape how the past possibilities arrange themselves. One way to imagine this is to think of a wave rippling forward from the past, a standard quantum wave function, and another, equally valid wave rippling backward from the future. The full description of a quantum event, in this view, lives in the meeting of those two influences. You only see the whole pattern when you know both where things began and where they end up. You can picture it like a story in a book that has already been written, cover to cover. You, moving through time, feel as if you are discovering the story one page at a time. You remember the earlier chapters and the later ones are unknown, but the book itself, sitting there on the table, contains every chapter at once. The beginning and the ending both quietly exist, whether or not you have read them yet. In a block universe view of space-time, something similar happens. Past, present, and future are all part of one vast four-dimensional structure, like a frozen sculpture of everything that ever happens. Your consciousness is like a small light moving along that structure, illuminating moment after moment, giving you the feeling of now sliding forward. From inside that experience, cause and effect feel like arrows. From outside, the pattern might be more like a web, with constraints running in both directions. That thought touches something sensitive in us, the question of freedom. If the future is, in some sense, already there, if it also acts as a boundary condition, what does that mean for your choices? When you stand in your kitchen, deciding whether to pick up your phone or leave it face down, is that a genuine fork in the road? Or is it more like turning a page in a book that has already been printed? Quantum retrocausal ideas don't give a simple answer. They don't crush free will, but they do invite us to loosen our grip on the simple picture where the past is fixed, the present is where things are decided, and the future is completely open. It might be that what we call a choice is how it feels, from the inside, when a particular path through space-time is traced out. The feeling of uncertainty, of not knowing what you will do, is part of that path. The equations don't tell you how it feels to be the character walking through the story. They only describe the structure of the story itself. And remember, even in retrocausal models, you still cannot send meaningful information into the past. The constraints run both ways, but they cooperate in such a way that paradoxes are avoided. You don't get loops where you warn your younger self, who then takes a different action that prevents the warning from ever being sent. Instead, you get something more subtle and, in a way, more unsettling, a universe in which correlations can be understood as coming from both temporal directions, without any single privileged now dictating everything else. Meanwhile, your everyday arrow of time, broken cups, and cooling coffee doesn't disappear. That arrow is tied to entropy, to the tendency of ordered states to spread out into more disordered ones, and to the very special, very low entropy state the universe seems to have started in. The feeling that time moves from before to after is still real and important. It simply may not be a fundamental law baked into the equations. It might be an emergent feature of how complex systems, like you, exist inside the larger structure. All of this leaves you in a curious position. On the one hand, your life unfolds moment by moment. The soft glow of a screen in a dark room, the weight of a blanket, the quiet hum of the world outside your window. You remember yesterday and anticipate tomorrow, and it feels obvious that one comes after the other. On the other hand, the quantum world hints that the story tying those moments together may not be written strictly from left to right along the timeline. The present may be shaped not only by what has already happened, but also by the way future events lock in and select certain patterns from the haze of possibilities. We don't yet know whether retrocausality is truly how nature works, or just one of several strange languages we've invented to make sense of the same experimental facts. Different interpretations of quantum mechanics give different stories. None of them, so far, has earned the right to be called the final word. What they do share is a lesson in humility. Time, which feels so simple from the inside, may be far more intricate than our everyday senses can grasp. The familiar arrow may be just a local shadow of a deeper, more symmetric structure, one that does not single out earlier and later the way our experience does. As you let your thoughts drift across that possibility, you don't have to arrive at a conclusion. You don't have to decide whether the future really helps write the past, or whether that's just a poetic way to talk about correlations in a timeless mathematical object. It's enough for now to imagine that the line of your life might be part of a larger pattern, one in which all moments coexist, quietly, like stars in a sky you can only see one patch of at a time. Imagine two people playing a game together, not online, not on the phone. They're in separate rooms with thick walls between them. No windows, no knocks, no shared screens. Before the game starts, they're allowed to meet. They can talk, they can plan, they can agree on any strategy they like. But once the game begins, the door closes, and from that moment on, they are completely cut off from each other. Here's how the game works. Each round, a referee walks into each room and asks a yes or no question. The questions are related, but not identical. Each player has to answer with either yes or no, or maybe red and blue, or +1 and -1. The exact labels don't matter. The important thing is that there are only two choices. Later, the referee looks at the two answers side by side. For some combinations of questions, the answers are supposed to match. For other combinations, they're supposed to differ. There's a fixed rulebook that decides what winning looks like for each pair of questions. The players know the rules in advance. They know what types of questions can be asked. They know how the scoring works. They just don't know which questions will be asked on any given round, and they cannot communicate once the game starts. Classically, this is just a logic and probability puzzle. The best the players can do, even with the cleverest shared strategy, is to agree on a set of answers that works well on average. They might decide, if I get question A, I'll always say yes. If I get question B, I'll flip a mental coin, and so on. You can write all of this down, analyze it, and prove that there's a hard ceiling on their success rate. Maybe it's 75%. Maybe it's a little less or a little more, depending on the particular game. But whatever that number is, there's a limit. No amount of planning can push their chances beyond that classical bound, as long as they're not allowed to communicate during the game. If they could send messages, they could coordinate and do better. But without communication, the ceiling is firm. Quantum mechanics, as usual, does not care about our ceilings. Now imagine the same setup, with the same two rooms, the same rules, the same inability to talk once the game begins. Except this time, the players are allowed to share something very special before they walk into their separate rooms. They are given a pair of entangled particles. Entanglement is one of those quantum words that can sound mystical, but here you can think of it as a kind of shared resource. The two particles are created together in such a way that their properties are deeply correlated. You cannot fully describe one without talking about the other, even when they are far apart. Each player takes one particle with them into their room. They agree on what they'll do with it. They decide that if the referee asks them a certain type of question, they will perform a particular quantum measurement on their particle and use the result to decide how to answer. Different questions correspond to different ways of measuring. When the game starts, the rules from the classical version haven't changed. The referees still choose questions at random, the players still can't talk. They only have their shared preparation and their entangled particles. And yet, when you look at the scores after many rounds, something astonishing happens. They beat the classical ceiling, not by a little, sometimes by a lot. In some carefully designed games, they can even win every single round, something that is mathematically impossible with any classical, pre-agreed strategy that doesn't allow communication. From the outside, it looks exactly like telepathy. Two people in separate rooms, apparently giving perfectly coordinated answers without any chance to exchange information. They're not signaling, they're not tapping on the walls. There's no hidden wire, no secret radio, no clever code. Just entanglement. This is what physicists call quantum pseudo-telepathy. It looks like mind reading. It looks like a shared intuition that never fails. But it isn't mind reading in the science fiction sense. No messages travel between the players during the game. In fact, if you examine either room in isolation, everything looks ordinary. Each player just sees a random stream of outcomes. Nothing about their individual data breaks any rules. The magic only appears when you bring the two data sets together and compare them. Then the pattern reveals itself. You find correlations that no classical explanation, based on local hidden instructions, can account for. One way to picture this is to imagine that in a classical world, every player's answers are like a stack of cards they prepared in advance. They shuffle the deck, but the deck is fixed. The best they can do is choose that deck cleverly. In a quantum world, entanglement means the deck is not really stored separately in each room. The two decks are part of one larger object. The shuffle on one side and the shuffle on the other side are not independent. They're connected in a way that can't be mimicked by any shared list of secret instructions created beforehand. Still, and this is crucial, no usable signal goes faster than light. You cannot use entanglement to send a message from one room to the other. You can't encode yes or no in your choice of measurement and have your partner read it out instantly. Every attempt to do that runs into the same wall. The local outcomes always look random. Only when someone later brings the data together in one place does the full structure emerge. So, what is being challenged here is not the speed limit of light, but something more subtle. Our assumption about how separate the world really is. In everyday life, we instinctively think of reality as local. What happens here should depend only on what's going on in the nearby region and on influences that have had time to travel here. If two people are in different rooms with thick walls between them, we feel safe in saying that whatever one does now cannot instantly affect the other unless there is some mediating signal. Quantum pseudo-telepathy doesn't break that safety rule in a direct way. It doesn't let you change your partner's immediate experience or send them a secret whisper through the vacuum, but it forces you to admit that the underlying story cannot be told using only local pieces that are glued together later. The universe in these experiments does not behave as if each particle carries its own private list of instructions that it consults when measured. The behavior of each particle depends, in a deep and irreducible way, on the entire entangled system, even when that system is spread out over distance. You might say, fine, but maybe there are still hidden instructions. Maybe we just haven't found them. The problem is that the games themselves are designed to test exactly that idea. The rules are set up so that any classical hidden instruction strategy will fail to reach the higher quantum score. When experiments consistently show that the quantum score is achieved, you are gently pushed into a corner. Either you give up locality, or you give up the idea that properties are well defined before measurement, or you accept a framework in which reality is not quite what our everyday language suggests. In a sense, these games are polite interrogations of the universe. They ask, is the world really made of separate pieces that carry their own properties, waiting to be revealed? Or is that picture just an approximation we use because it works well at our scale? Quantum mechanics doesn't answer in words, it answers in statistics. And the statistics say, if you cling to a classical, local, instruction-based story, you will get the predictions wrong. So, we're left with something that feels deeply counterintuitive. Two people, no communication, yet their answers line up in ways that no classical strategy can match. No telepathy, no magic messages, just correlations that seem to run through the fabric of reality itself, as if the separation between here and there is not as clean as we thought. You can sit with that for a while. Think about the people in those imaginary rooms, quietly giving their answers. Think about the long list of rounds, the columns of yes and no, looking perfectly random on each page until someone lays the pages side by side and the hidden pattern snaps into focus. Whatever reality is made of, it allows that pattern and forbids any classical imitation of it. That doesn't tell you what reality is. It doesn't give you a final picture, but it does tell you that our comfortable idea of a world made of separate, independent pieces, each minding its own business unless a signal passes between them, will never be enough. Entanglement reminds us, quietly and relentlessly, that the universe may be woven together more tightly than our everyday senses can feel. There's a scene in Alice in Wonderland where the Cheshire Cat slowly fades away. First the body goes, then the head, then the tail, until only the grin is left, hanging in midair. A smile with no cat. On the page, that feels whimsical and absurd, safely trapped in fiction. But in quantum mechanics, there is an experiment that sounds unsettlingly similar. It suggests that you can, in a very specific sense, separate a particle from one of its own properties. The cat seems to go one way. The grin seems to drift down another path. To get there, we start with something simple. A particle traveling through a device that splits its path in two. You can picture a kind of quantum fork in the road. A neutron enters, and the apparatus sends part of its wave function down the left arm and part down the right. If you let both paths recombine, you can get interference, places where the two parts of the wave reinforce each other, and places where they cancel. That's the familiar quantum interference story. Not just either left or right, but a superposition of both, until some measurement forces a decision. Now give the neutron an internal property. Neutrons have spin, a quantum version of angular momentum, a bit like a tiny bar magnet that can point up or down along some direction. So each neutron carries two things we can talk about: where it is, which path it takes, and how its spin is oriented. In ordinary thinking, those belong together. If the neutron goes down the left arm, then its spin goes with it, because the spin is a property of the neutron. You don't expect the magnet to stroll off down a different corridor. The Cheshire Cat setup asks, are we sure about that? The trick is to use something called weak measurements. Instead of slamming the system with a strong, definite measurement that destroys the interference, you probe it very gently, so gently that any single reading is almost meaningless. But when you repeat the process many times and average over a large ensemble of neutrons, subtle patterns begin to emerge. In the quantum Cheshire Cat experiment, physicists arrange the interferometer so that they can weakly check two different questions. Which path is the neutron taking? Where is most of the spin located? They also carefully post-select only those runs of the experiment where the neutron is detected in a particular output port at the end. They throw away the other runs and keep just the ones that match this chosen final condition. When they analyze the data from these selected runs, something strange shows up. The weak measurements that are sensitive to the neutron's mass, the there-ness of the particle, indicate that it mostly travels down, say, the left arm of the interferometer. The weak measurements that are sensitive to the spin, however, suggest that the spin is concentrated in the other arm. It's as if the neutron went one way, and its spin took the alternate route, the cat on one path, the grin on the other. Of course, nothing as dramatic as a little marble physically splitting apart is happening in the apparatus. No one opens the interferometer and watches a neutron body shuffle down one tube while a disembodied spin floats down the other. The effect shows up only in the statistical patterns of many, many carefully prepared and filtered runs. Still, if you try to describe what the experiment is telling you in ordinary language, you end up with sentences that sound like fantasy. Our classical intuition says that an object is something that has properties. You have a baseball with red stitching. You can toss the ball. It carries its stitches wherever it goes. You can't throw the stitches to the left and send the ball to the right. The idea that attributes might peel away from their owner feels nonsensical. Quantum mechanics pushes back on that picture. In these Cheshire Cat scenarios, the object and its property don't behave like a simple pair. They show up in different places in the bookkeeping of the experiment, as if what we thought of as a single, bundled thing is really a more delicate web of correlations. One way to interpret this is cautious and conservative. Nothing literally splits. The effect is a consequence of how weak measurements, superposition, and post-selection combine. You set up the experiment in a special way, ask very gentle questions, and then filter the outcomes. The numbers you get reflect how the wave function is distributed over possibilities. The separation is an artifact of the peculiar questions you're asking. Another way to look at it is more radical. Instead of imagining a solid little particle carrying fixed attributes from place to place, you treat the entire arrangement, the interferometer, the neutron, the measurement choices, as one unified quantum system. In that picture, the neutron is here and the spin is there, aren't descriptions of a tiny object with tags attached. They're statements about where certain kinds of information or certain kinds of influence show up when you probe the system. In that sense, the grin without the cat story becomes a hint that our usual nouns, particle, property, object, might be clumsy tools for describing the quantum world. They smuggle in assumptions about separateness and ownership that simply don't hold once superposition and entanglement are involved. Experiments of this kind have been done not just with neutrons, but also with photons and their polarization, using optical interferometers rather than matter waves. The technical details differ, but the theme is the same. You design a situation where a thing and one of its traits seem to drift apart, then use delicate measurements to reveal that mismatch. Does that mean there is a literal smile floating through space with no face behind it? Most physicists would say no. What it really means is that the quantum state is richer and more subtle than any picture built from tiny billiard balls with stickers. But even if you keep that sober, careful stance, there is still something quietly unsettling here. If a particle doesn't always keep its properties wrapped tightly around itself, what does it mean for anything to have a property at all? Is having even the right verb in the quantum world? Or are we seeing that properties only crystallize in specific contexts when certain questions are asked? You don't have to chase those questions to a final answer. There may not be one yet. It may be that we're still fumbling for the right language, the right metaphors, the right mental images. For now, it's enough to notice that even something as basic as an object with attributes is not guaranteed at the deepest levels of physics. The Cheshire Cat experiment reminds us that beneath the reassuring solidity of everyday things, there is a realm where even the link between an entity and its own features can loosen and blur. Somewhere in that realm, between the paths of an interferometer, the universe allows a story that sounds like a fairy tale, a cat that goes one way, and a grin that lingers elsewhere. There is a very old human wish hiding in the background of this story, the wish that somehow, in some deep way, your experience might never truly end. Not the body, not the cells, not the heartbeat, but that soft, private stream of awareness that says, I am. Quantum mechanics takes that wish and wraps it in something unsettling. It doesn't offer comfort. If anything, it turns the idea of never dying into a kind of quiet nightmare. To see why, we have to visit one of the most extreme interpretations of quantum theory, the many worlds picture. In the usual way quantum mechanics is taught, a system can be in a superposition of different possibilities. A particle can be here and there at once. A radioactive atom can be both decayed and not yet decayed. Then a measurement happens, and somehow the wave function collapses to a single outcome. One result becomes real, the others simply don't. Many worlds suggest that nothing actually collapses. The wave function keeps evolving smoothly. Every time there is a quantum event with multiple possible outcomes, the universe branches. In one branch, the atom decays. In another, it doesn't. In one branch, the detector clicks. In another, it stays silent. Each branch contains a complete version of the world, with a complete version of you, unaware of the others. In that view, what we call chance is really just which branch your conscious experience finds itself in. You never see the branches where you didn't end up. You only ever remember the path where your awareness continued. Now imagine pushing that logic to its harshest edge. Physicists call the thought experiment quantum suicide. The name alone is a reminder that this is not an experiment for real life. It is a purely hypothetical scenario, disturbing by design, used to probe the connection between quantum theory and personal experience. No one should ever attempt anything like it. In the real world, death is final, irreversible, and unimaginably painful for everyone around it. The setup goes like this, in its simplest description. A person sits in a sealed room with a device that is triggered by a quantum event, a true 50-50 outcome at the deepest physical level. If the event goes one way, the device does nothing, and the person lives. If it goes the other way, the device kills the person instantly. From the outside, this is just a terrible version of Russian roulette. Each trial has a 50% chance of survival. After enough repetitions, the probability of the person still being alive becomes vanishingly small. Classically, you would expect them to die fairly quickly. But in the many worlds picture, something different is happening in the background. Each time the quantum event occurs, the universe branches. In one branch, the device fires and the person dies. In another, the device does nothing and the person remains alive. From the viewpoint of a family member or an observer outside the room, most branches are tragic. They see a sequence of trials ending in death, just as ordinary probability would predict. From the first-person perspective, though, the story is stranger. The only branches this person can ever experience are the ones where they survive. There is no conscious awareness in the worlds where they died, because there is no longer a living observer there to register anything. Subjectively, they might hear the device click, see that they are still alive, and decide to try again. The odds get worse and worse on paper, but in their own memory, they keep waking up in the branch where the coin flip spared them. This leads to the idea of quantum immortality, the claim that if many worlds is true, your conscious experience would always find itself in some branch where you survive, no matter how unlikely. You would never personally reach a moment of non-experience. The sequence would go on in a thinning set of branches where, against all odds, you always somehow make it through. At first glance, that might sound like a bizarre form of comfort, a whisper that says, some version of you makes it every time. But seen more clearly, it is anything but comforting. Because the branches where you survive, repeated impossible odds, are not warm or gentle places. They are the worlds where things have gone increasingly wrong, where life keeps twisting itself into more improbable and lonely shapes. You could end up in a reality where almost everything familiar has fallen away, where you were surrounded by outcomes that were astronomically unlikely, simply because those are the only ones in which you are still present to notice anything at all. Immortality of that kind doesn't look like a peaceful eternity. It looks like a drawn-out drift into increasingly isolated, fragile branches of reality. On top of that, there are deep questions about identity. If the universe splits into countless versions, and each version of you feels like the real one, what does it even mean to say, I continue? Are all those branches equally you? Is survival in some remote, wildly unlikely timeline the same as your survival in any meaningful sense? Many philosophers and physicists are skeptical of the entire quantum immortality idea. They point out that many worlds itself is still an interpretation, not a proven fact. They argue that the thought experiment stretches the interpretation far beyond what the equations actually require. It smuggles in assumptions about consciousness traveling along a single line of experience, hopping from branch to branch, when the mathematics doesn't explicitly say that. And behind all of that is the very real ethical line. The scenario is meant to test ideas about quantum theory, not to suggest anything about how to live. In the real world, playing games with survival is not a philosophical puzzle, it's a tragedy. People are not test subjects for metaphysical speculation. So, what remains once we strip away the shock value? Quantum suicide and quantum immortality sit at the intersection of physics and our deepest fears. They force us to confront how fragile our ideas about self really are. They highlight something unsettling about probabilistic theories. From the outside, you can talk about chances and branches and measures. From the inside, you only ever feel one continuous line of moments. These thought experiments don't tell us that we secretly live forever. They don't rescue us from mortality. Instead, they show how easy it is to bend our intuitions when we mix personal experience with the strange logic of quantum mechanics. Maybe the most honest thing to take from them is a kind of quiet humility. Our best physical theories can push us into regions where words like life, death, self, and future stop behaving the way we expect. The equations reach into places our everyday language was never designed to map. Out beyond those equations, though, there is still the ordinary human fact of a finite life, moving through its days and nights, aware for a little while in a vast, indifferent universe. That limited arc may be more precious than any imagined eternity in exotic branches of the multiverse. In that sense, the disturbing logic of quantum immortality does something strange and gentle at the same time. It reminds us that whatever this stream of experience is, it is fragile, temporary, and deeply mysterious. And it invites us to sit with that mystery, not as a promise of endless survival, but as a reason to breathe a little more softly into the time we actually have. Far away from the quiet room you're lying in, there are places in the universe where the rules we trust begin to argue with each other. Not in a small way, like a tiny correction or a rounding error, but in a deep, stubborn conflict about what can and cannot happen. Black holes sit right in the middle of that fight. If you follow Einstein's general relativity, a black hole begins with something very familiar. A massive star running out of fuel. It can no longer hold itself up against its own gravity. The star collapses, shrinking and compressing until the pull becomes so intense that not even light can escape. The boundary around that region is called the event horizon. Cross that line, and every possible path forward curves inward. There is no route back out into normal space. From the outside, black holes seem strangely simple. According to the no-hair theorem, if you wait long enough, the only things you can know about a black hole are its mass, its electric charge, and its spin. All the rich details about what fell in, the pattern of atoms, the shape of a planet, the complexity of a book or a brain, are smoothed away. Different histories can lead to exactly the same final black hole. Quantum mechanics, however, lives by a different rule. In the quantum world, information is sacred. The exact configuration of a system at one moment is encoded in its wave function, and that wave function evolves in a way that can, in principle, be reversed. If you had perfect knowledge, you could wind the dynamics backward and recover how things used to be. Probability flows around, but it doesn't simply vanish. At a deep mathematical level, quantum evolution is supposed to be information preserving. So gravity says, black holes erase details. Quantum theory says, fundamental processes never do. For a long time, that tension stayed in the background. Then Stephen Hawking pushed the two theories together in a serious way. He asked what happens if you treat fields near the event horizon quantum mechanically, while keeping the space-time itself described by general relativity. The calculation he did in the 1970s led to a surprising answer. Black holes should not be perfectly black. Instead, the vacuum around the horizon should glow faintly. Quantum fluctuations allow particle-antiparticle pairs to appear and disappear near the boundary. Under the right conditions, one member of the pair falls in, while the other escapes, carrying away a little bit of energy. To an observer far away, this looks like the black hole emitting radiation, now called Hawking radiation. Over immense stretches of time, this slow leak adds up. The black hole radiates energy, shrinks, and eventually evaporates. A massive star collapses, forms a black hole, and then, drop by drop, the black hole disappears again into a bath of thermal radiation spread across space. And here is where the paradox bites hardest. According to Hawking's original calculations, that radiation is featureless. It depends only on the mass, charge, and spin of the black hole, not on the specific details of what fell in. If you throw in a piano, a planet, or a complete library, the Hawking radiation that comes out later carries no trace of which one you chose. When the black hole is gone, all that seems to remain is a random cloud of photons with no memory. From the viewpoint of quantum mechanics, that looks like genuine information destruction, Many different initial states collapse to the same black hole, and that black hole evaporates into the same thermal haze. There is no way, even in principle, to reconstruct what originally fell in. A unique past has turned into an ambiguous blur. The clean, reversible flow of the wave function appears to have been broken. If that really happens, the foundations of quantum theory start to shake. Probabilities stop adding up properly. The neat, unitary evolution that underlies the theory would have to be abandoned or heavily modified. On the other hand, if information is somehow preserved, then the way we think about space-time and general relativity can't be quite right. One of our best theories is lying to us, or at least hiding an important piece of the truth. For decades, physicists have been trying to escape this trap. One possibility is that the information does leak out, but in a way that is incredibly subtle. The Hawking radiation might not be perfectly random after all. Tiny correlations between the outgoing particles, spread over vast time scales, could encode what fell in. To us, with limited detectors and finite lifespans, it would look like ordinary thermal light, but in principle, someone with impossible precision could decode the pattern. Another idea takes a more radical step. Maybe the information is never inside the black hole in the way we imagine. The holographic principle suggests that everything happening in a region of space can be described by degrees of freedom, living on the boundary of that region. In the black hole case, that boundary is the event horizon. All the information about what has fallen in might be stored on the surface, like bits on a cosmic hard drive. The interior is then not a separate place with its own independent contents, but a different way of organizing the same data. This picture leads to a very strange vision of reality. A three-dimensional volume full of stars, gas, and people could be equivalent to a two-dimensional pattern of information written on a distant surface. What you think of as inside might be more like a hologram projected from the edge of space-time. Trying to protect both information and the smooth geometry predicted by relativity leads to further puzzles, like the so-called firewall paradox. If information escapes in the Hawking radiation in the right way, some arguments suggest the horizon cannot be a gentle crossing for an infalling observer. Instead of drifting through without noticing anything special, they might hit a violent region of high-energy excitations, a firewall that tears apart both the traveler and the comfortable picture of curved space-time. Each resolution seems to demand a sacrifice. Give up information conservation, and quantum theory loses its core structure. Give up a smooth horizon, and general relativity's calm description of free fall fails. Give up the usual idea of locality, of events happening at specific points in space, and you enter a more non-local universe, where what happens here is deeply entangled with what happens there. No one has yet written a final answer in the sky. There are frameworks, hints, partial results, and beautiful conjectures, but not a clean, agreed-upon story. For now, the black hole information paradox stands as a reminder that even our best theories are, in some places, talking past each other. And somewhere out there, at the center of a dark galaxy or the heart of a quiet quasar, a black hole continues to glow faintly into the void, slowly evaporating over unimaginable ages. To us, it looks silent and simple. Behind the silence, it may be encoding, scrambling, and releasing the history of everything that ever crossed its horizon. Whether that story is perfectly preserved or truly lost is still an open question. But the very existence of the paradox tells us something profound. When gravity and quantum mechanics finally learn to speak the same language, our picture of reality will almost certainly change in ways that feel as strange and as unsettling as the black holes that forced us to ask these questions in the first place. For a moment, let your mind drift back over everything we've talked about so far. Double slits that seem to care about our choices, observers who don't agree on what really happened, games that can only be won with impossible correlations, black holes arguing with the laws of probability. There is a quiet thread running through all of them. Before we look, The quantum world is described as a cloud of possibilities. An electron is not here or there, but in a superposition of both. A spin is not up or down, but suspended between those options. The equations give us a smooth wave function that evolves in time, spreading, interfering, combining. Nothing in that math ever says, now choose one. And yet that is not how we experience the world. When we actually perform a measurement, we never see a blur of maybes. We see a definite result. The detector clicks in one place, not in all the places where the wave function said it could. The spin meter shows up, or down, never the strange in-between that the math happily allows. This gap between the flowing wave of possibility and the hard edge of a single outcome is the measurement problem. What exactly counts as a measurement? Is it the moment a particle hits a screen? When a macroscopic device amplifies that tiny event? When a conscious observer becomes aware of the reading? Or does the universe choose long before any of that? Different interpretations answer in different ways. In the Copenhagen view, the wave function is a tool for predicting outcomes. It collapses when we measure, full stop. But the line between quantum system and classical apparatus stays blurry. In many worlds, there is no collapse at all. The wave function never stops branching. Every possible outcome happens somewhere, and you simply find yourself on one branch, wondering why that result and not the others. Decoherence explains why interference fades when a system leaks information into its environment, but it still leaves a lingering question. Why do we experience one outcome instead of a superposition of them? Objective collapse models imagine a genuine physical process that snaps possibilities into a single reality. But direct evidence is still elusive. Ideas that tie collapse to consciousness try to place the mystery inside the mind itself, tempting, controversial, and very far from settled. We trust the equations because they work with astonishing precision. We just don't yet agree on what they are really telling us about the world that feels so solid under our feet. As we start to drift toward the end of our little journey tonight, it can be helpful to look back over the strange landmarks we've passed. We visited the delayed choice quantum eraser, where the future seems to reach back and help decide how the past should look. We met Wigner's friend, standing in a closed lab, quietly insisting on a reality that doesn't match the one seen from the hallway outside. We played with retrocausality, where time begins to feel less like an arrow and more like a whole structure written at once. We watched players win impossible games with quantum pseudo-telepathy, acting in perfect sync without ever sharing a word. We followed the quantum Cheshire cat, where a particle's smile appears to wander away from the particle itself. We sat with the unsettling idea of quantum suicide and quantum immortality, where consciousness seems to ride the branches in which it never quite goes dark. And finally, we stood at the edge of the black hole information paradox, listening to gravity and quantum theory argue about whether information can ever truly be lost. Each of these paradoxes is a crack in the story we tell ourselves about reality, but cracks are also where light gets in. In the past, puzzles like these have changed everything. Mercury's odd orbit nudged Einstein toward general relativity. The failure to explain the spectrum of light from hot objects pushed Planck, then Bohr, then Schrödinger and Heisenberg toward quantum mechanics itself. So, when the current picture stops making sense, that may be the universe's way of pointing at the next page. Paradoxes are not just embarrassing bugs in the code of physics. They are signposts, quietly marking the places where our understanding is too small. Quantum theory might not be the final word, just a powerful middle chapter in a much larger book we're still learning how to read. For tonight, it's enough to know that it's okay not to have all the answers. You can let the questions rest for a while. Feel your breathing slow, feel the weight of your body sink into the mattress, and imagine the universe gently humming along, full of mysteries that don't need to be solved before you sleep. Thank you for spending this time here. Whenever you're ready, you can let your thoughts fade. Let the paradoxes soften into background noise and allow yourself to drift. Sleep well.